Hello everyone, I'm Wang Liangdao. Today I will talk to you about our research, deep hashing with minimal distance separated hash centers. This sharing will be divided into the following 5 parts. First of all, our research task is image hashing retrieval. In this task, we use one image to search the similar image from the database. Image hashing retrieval is popular due to its highly efficient storage ability and retrieval speed. Image hashing methods encode the image into hash codes and use the Hamming distance to calculate the similarity between two hash codes. The following picture is the process of searching image in the database. We adopt the Gilbert bound from coding theory to generate a set of hash centers. With these hash centers, we propose a two-stages hashing model with the effective loss function to generate hash codes. When the hash length is 16 bits, the proposed method displays a relative improvement of 9.6% and 7.1% compared to the best baseline on NA burst and Stanford cost. In terms of the training process, supervised deep hashing methods can be divided into pairwise methods, triplet-based methods, and point-wise methods with hash centers. We usually use mini-batches to train deep hashing networks. Therefore, the pairwise methods and the triplet-based methods construct image pairs or triplet in the image batch. Such construction approach will cause an issue that the number of positive pairs and negative pairs are imbalanced. For example, when the batch size is 128 and the class number is 64 on average, one mini-batch only has 2 points from each of the classes, which means few positive pairs are constructed. Recently, some point-wise methods like CSQ construct one hash center for each class and use these hash centers to guide the training of hash networks and make the hash codes of images get close to their corresponding hash center. Such point-wise methods have high training efficiency, can learn global similarity distribution of data, and has no issue of pair imbalance. Next, we will introduce our method. Recently, the representative hash center generation method like CSQ use hardware matrix and Bernoulli sampling to construct hash centers. However, such construction methods have an issue that the distance between some pair of hash centers can be small. For example, the Hamming distance between the hash codes in the third and ninth columns in the figure is 0. This motivates us to generate minimal distance separated hash centers. In our work, we propose a new hash center method to ensure that the Hamming distance between any two centers is no less than a minimal distance d, and d is larger than 0. Now I will introduce our proposed model. The proposed hashing model can be divided into 2 stages. In stage 1, based on the Gilbert boundary theory, we employed an optimization procedure to produce hash centers constrained by a minimal Hamming distance. In stage 2, we employ a deep hashing network with 3 loss functions to generate hash codes. Firstly, in stage 1, we find the largest minimal distance that satisfies the Gilbert bound by exhaustively searching from 1 to q. The Gilbert bound is shown in equation 1, which guarantees that as long as the class number c, hash bit q, and d satisfy the equation 1, there is 6 CQ bit codes that the minimal Hamming distance between any two codes is no less than d. Then we propose the optimization object like equation 3 to maximize the average distance between every two hash centers and guarantee that the Hamming distance between any two hash centers is larger than d. Because there are binary constraints on hash centers, alternately, when we update one hash center, other hash centers are fixed. Besides, we apply the LP-box ADMM algorithm to change the binary constraints to the real constraints. Finally, we use ADMM algorithm to update Hashi centers HI, some variable ZI, and log-range multiplier YI. In stage 2, we build a deep hashing network which consists of 3 blocks. The first block is a ResNet 50 backbone. The second block is a HashiCorp layer. The third block consists of 3 loss functions, including loss towards Hashi centers, loss for similar pairs of the same Hashi centers, and quantization loss. Finally, we combine the 3 loss functions with hyperparameter lambda 1 and lambda 2. We evaluate our method on 3 datasets and use MAP and PR curve as evaluation metrics. Firstly, we compare our method with other hashing network methods. The comparison results can be seen in the table. As shown in the table, the proposed method outperforms all the baselines on 3 datasets, especially when the HashiCorp length is short. We also compare with other Hashi center generation methods to validate the effectiveness of our method. We use CSQ as our baseline. We can find that our method performs better than the baseline method, and the minimal distance meets the Gilbert boundary theory. Finally, we validate the effectiveness of loss functions and find that each loss function plays a certain role in improving the retrieval effect. We can draw a conclusion that represents an optimization approach for producing Hashi centers with Gilbert bound and propose effective loss functions to chain deep hashing networks. Empirical evaluations shows that the proposed method outperforms the state-of-the-art methods. That's all. Thank you for your listening.